Hello, class. Welcome. Today we're going to start chapter 1. The first section that we're going to discuss is 1.2, finding limits graphically and numerically. All right, so we are going to define what does it mean to be a limit. We're going to show you how to find these limits graphically and also numerically. The objectives is to estimate a limit using the numerical method or the graphical approach. And then we're going to discuss how to learn different ways that a limit can fail to exist. And then we're going to show the study and the use of a formal definition of a limit. So first of all, let's jump in. Let's introduce the definition of a limit. So the limit definition is very um, analytically. It's a definition that is very close to the way the language is using calculus. So we're gonna go back and sort of review a little bit of our algebra, and then we'll along the way we'll discuss the new definition. So the first goal is to find the limit of this function as x approaches 1. All right, so first of all, what does it mean to approach, what does it mean for x to approach 1? Well, x lives in this number line right here. Now, x equals 1 is specifically here. Now, if x is a variable, so it could be the value of x can vary along a number line. That's how we define a variable. So x could be 0, x could be -1, x could be -2, x could be 1, x could be 0.5, x could be 0.9, and so on, right? They're all x values. And so when we are describing an approach, we are defining x is approaching 1 means that x values represents values that are getting closer and closer to 1. But as we know, since it is a two-dimensional number line, you can also approach it from the right side. So you can approach 1 from the right side as well. And that's how we're going to define approaching. Right? And of x is approaching 1 means that it is approaching from the left side and it is approaching from the right side, right? It's just these numbers that vary and getting closer and closer to 1. That's what it means to be x approaching 1. And then to find the limit of a function, the value of the limit of a function will vary depending on which value we are approaching to. So for example here, if the goal is to find the limit of the function, and so this is the first time we're looking at this definition or this notation, what this is reading is we're finding the limit of what? Of the function as x approaches 1. So we're going to try to figure out what does that mean contextually, right? What does that mean in this mathematical? And it's actually pretty straightforward. Remember that x represents the y values. Now, how do we measure y values? We measure y values by going up and down, right? Those are the y values. As we know that the x values go left and right. So if we're trying to figure out what is the y value approaching as your x approaches 1, what that means is that we're looking for what is the value approaching in the sense of up and down as the x value is approaching 1. Well, remember that this function right here represents all x values, x's and y's, x's and y's, x and y's, x and y's. And for that, I can actually give you guys a good tool here. So I'm going to pull out my decimals, as you see here, and I already have embedded that function in here. And so I want to remind you that this value of the function represents a bunch of x's and y's. For example, here you'll see that this x is negative 2.3, comma 3.9. If I go all the way over here you can see how that changes, right? Negative 0.35, and the y value is 0.772. I just moved it, but anyways. And then if you notice here, right in that moment, x is 0, y is 1, right? And these x's and y's have a relationship that is defined through this function. So anyway, so we can clearly see that this function is just a bunch of x's and y's, right? And so the goal is to figure out what is the y value approaching, right? What is the y value? Here's the y value. This is at this point, right? At this point, x equals 0, y equals 1. At this point, x equals, let's see, what is that equal to? Somewhere in here, right? That's close to 0.2. Somewhere, right? X is 0.64, y is 2, right? Somewhere in there. Anyways, and then so if you get closer and closer and closer, what we want to figure out is as the x value gets closer and closer and closer to 1, what is the y value approaching? So for example, as x approaches 1, what is the y value of this, right? That's what we're trying to figure out. And so what we're going to do is that in some cases there will be holes, like in this example, right? That's why I put this example, because there is a hole, there's a missing value. In fact, if we try to figure out what this value is and we plug in 1 in here, what we're going to get is 0 over 0. Now this, we're going to be able to sort of understand the meaning of 0 over 0 later on, and we're going to learn that this in fact gives us a hint. But for now, for this section, we're going to take the approach of a graph, the numerical and graphical approach. So what we're going to do is we're just going to use tables, and we're going to use a graph to kind of give us a sense of what's the limit of the function. Of course, using a graph is not the best way to find a limit, but it is a one way. And this approaching it this way for now give us a little more of sense of understanding of what is the limit mean. Later on, we're going to find out, again, a better, faster, practical way to find a limit. So the way we're going to find the limit, our goal is to find out is what is the value of the function approaching as x approaches 1. And let me maybe put this like this. So as x approaches 1, f of x is approaching what? And then and what I mean by x approaches 1, this is the notation that we have. It means you get close, right? Closer. As x gets closer to 1, f of x is getting closer to what? Now remember that this means the y value. So here we have a table. We're going to plug in numbers that are getting closer to 1. And if you guys notice here, we have 0.75, it's close to 1. 0.9 is even closer to 1. 0.999 is even closer to 1. 0.9999 is even closer to 1. And then 1, of course, it's 1, right? But even then, we notice that we're also going to approach 1 from the right side. So we're gonna try 1.25, 1.1, and if you notice, we're getting closer and closer to 1. And so for this, we're gonna go ahead and plug in these numbers in our function, right? We're gonna plug in x equals 0.75 here, meaning for every x, and the outcome will be this value. Then we plug in 0.9 here, right, for x, right? And the outcome of this is this. You input this into the function, and the outcome is this. So at this point, I'm gonna go ahead and jump into Desmos over here, and I already have this this table set up for us, and you guys can see how I plugged in these numbers on the left side. And if you notice, the numbers are that I plug in x are getting closer to 1, right? Even I plug in 1, and what do we notice? That the number of the value of the function is undefined, right? But what we are interested here is seeing what is the value of the function approaching to. In other words, where is y approaching? Well, if you notice, as you notice here, as x gets closer to 1, right? I'm gonna move my cursor. But if you guys notice, as you get closer to 1, the first component, in this case 0.317, is getting bigger and bigger and getting closer to 1, getting closer to 1. But as you notice, I'm getting closer to 1, 0.75, 0.867. The number of y is getting actually closer to some number. What is that number getting close to? Well, you can try a guess there. We can try a guess. And as I get closer to 1, the number is getting close to, you see, 0.99. That's very close to 1. And the number on the right, 2.97, is getting closer to 3, right? And then the same thing happens over here, right? If I come from the right side, 1.416, 1.37, 1.33, 1.223, and the number on the right is getting 3.78, 1.2, and now we have 3.64. As I get closer, 1.09, and then the right side number is 3.278. I get closer and closer and closer and closer, and then 1.036, and then the number that I have on the right is 3.16. So if you notice from both directions, as my x value is getting close to 1, my y value is getting closer to 3. And that's it. That's it. That was the limit. We just found out that the limit of this function is 3. That's all we were looking for. So we can come back over here, and then we can write the value of 3. Now, in order to be a limit, and this is the one of the important conditions or properties of a limit, is that the value of the function does not have to exist. As you guys can see here, it does not have to exist in order for the limit to exist. And that's sort of the big deal, right? All right, so now we're going to start using this notation more often. And so the way you probably want to think about it is that the value of f of x becomes arbitrary close to a single value number L, in meaning y is getting closer to some number L, and x as x is approaching some number c from either side. Then the limit of f of x, as x approaches c is L. So the number L is the limit, right? The limit L is the limit. So 3 is the limit of f of x. So in other words, what we're saying is this. And this is how we want to maybe think about it. As x gets close to 1, the y value gets close to 3. Right? As x gets close to 1, the y value gets close to 3. That's what we're looking for. That's all we're looking for, right? And again, I want to emphasize that the value of the function at x equals 1 does not exist, as we see that little hole there, right? All right, so let's move on to another example. Example number 2, now we have a function that is x all over the difference between the square root of x plus 1 and 1, right? And we're looking for the limit of this function, right, as x approaches 0. In other words, we're looking for what is the y value. Maybe I'll write it here. As x gets closer to 0, as x gets closer to 0, then y, in other words, your f of x, y gets closer to what? Y gets closer to what? And then we can see that in the picture. We can see that in the table. And I'm doing the same thing over here. I have a in Desmos the same example, another example that we can work on. And so we see it here, right? So it's the same problem. As x gets closer to 0, so here we are. You can see my blue dot is getting closer and closer to 0. The value of y goes up, goes up, goes up, and as x gets closer to 0, the y value gets getting close to 2, right? And now as x goes closer to 0 from the right side, right? From the right side, it's getting smaller, right? But the value of y is getting closer and closer to 2, right? As x gets closer to 0, the y value gets closer to 2. And that's we can see evidence that in the equation. If you guys want to see this closer, you see how we can even get closer and closer and closer and closer and closer. As x gets close to 0, y gets closer to 2. And so here we can see that in the table, we would have be able to recognize that as well by looking at the table. Now, graphing is very hard to be precise. So it's very practical that instead of drawing a graph is that we use an actual table, right? So if I'm not giving you the graph, don't make the graph, make a table. And so the numbers you're going to plug in are numbers that are getting closer and closer to 0. Closer and closer to 0. So you're trying to mimic this, right? Your x is approaching 0 from left and right, and you notice that f of x is approaching 2 from on both cases, right? So what we're going to say here then is that as x approaches 0, the value of function is approaching 2. And again, we don't the value of the function is actually undefined at x equals 0. We know it's undefined. We can see that because there's a hole there. But nonetheless, the limit does exist. There's still a limit, right? And again, that's one of the benefits of talking about the limit. It's one of the benefits of talking about the limit. Now, we have talked about that every single time we must look for both approaches, right, from the left and the right. And you might be thinking, we haven't had an example where it hasn't given us a different number, right? And so the next example sort of give us the evidence that we need to comprehend that we actually have to check both sides. So we do have to check both sides, as we're going to see in this upcoming example. So let me try this example now. So here we ask you to find the limit of the absolute value of x over x as x approaches 0, right? Show that this does not exist. Now in this example, what we have here is that f of x is this part right here, right? The absolute value of x over x. So that's how you're gonna treat that as your function. And we're gonna do the same approach. We're gonna create a table. And then we're gonna graph it here. So I took the same approach, right? I created a table, and you guys can see here that in my table, I plugged in negative 0.1 because we're getting closer to 0, right? So negative 0.01, negative 0.001, and then I plug in 0, and we can see that it's undefined. So next one is 0.00, positive 0.001. Next one is positive 0.01. Next one is positive 0.1. And if you notice something particular about this is that the y value for each of these cases was actually -1, and for the second part it was always +1. And we can kind of see here that that's sort of interesting, right? And so as we gonna talk about in this example, as x approaches 0, so maybe I'll write that over here, sort of kind of what we've done before. As x approaches 0, f of x is approaching what? In other words, your y value is approaching what? And so what we're gonna see is that it's evidence that the value that this is approaching to is actually going to be, as x approaches 0, let me give more space here. As x approaches 0 from the left side, the value is always -1, -1, -1, -1, -1, -1, and then it jumps. And then now from the right side, right, as x approaches 0 from the right side, the value of y is always 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, except at that moment, right? And I'm not seeing why this is here. Maybe I'll move that up here. There you go. And that way we can kind of see this holes, right? Those two holes there. Anyway, so we can see here that in fact that the value of the function, here is actually approaching two different values. It's approaching -1 when as x approaches as x approaches 0 from the left side. And we actually have a special notation for that is approaching from the left side. We have this, like, it looks like a power, but it's just a minus. It's just a special notation that we have in calculus that tells us that we are approaching from the left side. And then f of x is approaching +1 as x approaches 0 from the positive side, from the right side. So left side, right side. Right. So if we notice here, it is not approaching the same value, and that's sort of the actual definition of a limit. In order for the limit to exist, it must approach the same value. So in this example, the limit of this value of this function as x approaches 0 does not exist, because it does not approach the same value. And that's it, right? That's the whole thing. And so we go over that in this notes. But so what are you gonna show me? And what do you need to show me as a student that you have proven that this does not exist? Well, what you need to show me is the actual table, right? So you're gonna create that table. You're gonna say x and f of x. So you're gonna plug in -0.1, -0.01, -0.001, and then 0, and then the same thing, 0.1, 0.01, 0.001. And then here, this was -1, -1, -1, 1, 1, 1, right? And this is what you will show me. All right, so you show me that the limit does not exist. Right, so that's pretty much it to show me, right? So again, you're not expected to graph it. In fact, that's too complicated to do, and as a if we don't have a computer based calculator, then it will be very hard for you to actually be accurate. So the way we're gonna be approaching it is by making tables. Tables are very easy to make, and often we can just type it in a calculator just to get those actual numbers. All right, so moving on. So we have defined now the limit. We know when a limit exists and when a limit does not exist. So we said the limit exists when the value of the function as x approaches c from both sides approaches the same value, right? It has to approach L as some specific value. If it approaches two different values, then that means the limit does not exist. Here we actually have a few more cases. So the first one is the one that we just talked about. F of x approaches a different, so common types of behaviors associated with non-existence of a limit. The first one is if f of x approaches a different number from the right side of c, then it approaches from the left side of c, right? As x approaches c from the left and the right, we have the value of the function approaches two different values, right? Two different values. The other one is that if f of x is increasing or decreases without bound as x approaches c. An example of that will be something of this form. And if you guys remember, in pre-calc, we talked about the asymptotes, right? We had asymptotes. And if you guys remember, in those cases, let's say I had this y equals 1, x equals -2, x equals 2. And we had a graph that was either going something of this form, and then we had this graph going something of this form, right? And then maybe I'll just do the same thing over here, right? So these were asymptotes. And so what we're saying here is that as x approaches 2, right? As x approaches 2 from both left or right, it doesn't matter. We notice that the value as x approaches 2 from the left, the value of the function is actually increasing without bound. We can argue the same thing, right? We don't even have to argue anymore because we just showed it that on the left side it was approaching f was increasing without bound. But we can see here that it's decreasing also without bound as x approaches 2 from the right side. So that's what that means for number 2. The number 3, it's a different case. In that case is something of this form. So let me draw a graph here. And this will be the case where you have a graph that behaves sort of in a oscillation. And what I mean by that is that the graph maybe goes like this, and then it goes like this, and then somehow it just stays with that, right? It just stays with that. And then it goes like this, and it gets closer and closer and closer, and then it starts getting bigger and open, and like that. So what happens here is that as x approaches 0, the value of the function is inconclusive, right? Because it's actually, it could have gone to either this value or that value, right? So it was going up or it was going down. So that would be the third case, and that's known as f of x oscillates between two fixed values as x approaches c. Okay, so the next example that we have here is the we're gonna talk about the formal definition of a limit, and this might be we don't want to talk too much about this because this is very technical and very abstract. But it's very important for us to actually have a good idea, and I mean idea of what this means, right? So what we have talked about so far is not the formal definition, but instead more like an application of the limit. The formal definition of a limit has to do with the concept of approaching, right? What does it mean to approach something? Mathematically speaking, I mean, we can contextualize, think that something approaches something, it means that something that are getting close to each other. Now, mathematically speaking, how do you translate that? Well, that means that the two distance between the two numbers is getting smaller. Well, smaller means the difference between those two numbers is small, right? And that's sort of what the actual definition comes from, right? So let's take another look at the informal definition of a limit. If f(x) becomes arbitrarily close to a single number L as x approaches c from either side, then the limit of f of x as x approaches c is L, which is written like this, right? This is the informal way. At the first glance, this definition looks fairly technical. Even so, it is informal because exact meanings have not yet been given to the phrases. Of f of x becomes arbitrarily close to L. We haven't defined what that means mathematically as x approaches c. So the first person to assign mathematically rigorous meaning to these two phrases was Agustin Louis Cauchy. So his approach was that using epsilon and delta definition of a limit, and this is a standard use today. So in the figure below, you will see the value epsilon, which is a lowercase Greek letter that represents a small positive number. So epsilon, think about is like a number that is very small, such as, think about the small number you can think you want 0.0005, right? That's a small number. And then the phrase f of x becomes arbitrarily close to L means that the f of x lies within an interval that is very small. And the way I can sort of describe what this means is that that if I make this line, that if I have my L here, and I'm gonna make a boundary, right? This boundary, this interval is going to be L minus epsilon, and this upper interval will be L plus epsilon. And so what this means is that f of x lies within here. In order for f of x to be close to L, means that it has to be within here, right? Somewhere in here, right? As x approaches, as x gets closer to c, the f of x value gets closer to L, right? The closer this is, the closer this is, right? That's what it means if there is a limit, right? If f of x has a limit of L. So as x gets closer to c, f of x gets closer to L. And what we're saying is that if the limit exists, f of x lives within these boundaries, right? Where epsilon is very small. So L is like a number like 4. If I say this is 4, right? If I said this is 4, and then we have 4 minus epsilon, or 4 plus epsilon. And if I said that epsilon is 0.005, then what we have here is 4.005. And here we have 995. And so if you notice, if this is true, right? If x is closer to, let's say, 9, right? Then the value of the function implies it's very close to 4. And so it lives within these boundaries. That's what we're trying to say with this. And so the way we would write this mathematically and formally will be by saying that the difference between f of x and L is very small. The difference between f of x and, let's say, 4 is very small, like this, right? That is very small. That these two values are very small to each other. They're very close, so therefore the difference between them is very small. Now, it's more important for us to use the absolute value because we want to establish the case where if f of x is bigger than 4, the difference between those two will be positive. But if f of x is smaller than 4, then this difference will be negative, and we just want to keep this value to be positive all the time. So that's why we put this absolute value. And then so in the similar approach, we can say that x is approaching c means that there exists a positive number delta such that x lies in either the interval c minus delta and c, or the interval c and c plus delta. In other words, what we're saying is that x minus 9, x plus as x approaches 9, means that um, that if delta is, let's say, 0.001, then as x approaches 9, then we have nine minus delta and 9 plus delta, and this will be 9.001, and this will be 8.999. And we're saying that x are values that are within these boundaries, right? X are values within these boundaries. So very close. We're saying that x is within those boundaries. And so the difference between those two is smaller than 0.01. So if you notice here, the difference between those two is 0.001. The difference between those two is 0.001. So x and 9 have smaller difference, right? The distance between those two is even smaller. And remember that in pre-calc, we learned that a best way to describe the distance between two objects is by using the absolute value and the inequality. So for now we're gonna discuss the actual definition of a limit, and the actual definition of a limit is written in this form. If f is a function defined on an open interval containing c, except possibly at c, and let L be a real number, then the statement the limit of f of x equals L as x approaches c means that for any epsilon greater than 0, you can find a delta greater than 0, such that if the absolute difference of x and c is less than delta, this will imply that f of x and L must be smaller than epsilon. Okay, so what does this mean? What this means, and I can sort of use this example here, is we're saying that if this is small enough, how small? Delta small. The difference between those two is small enough. That means the difference between those two should be small enough, right? That's what this is saying. If the limit exists, then that should be true. If the limit exists, then that should be true. And what I mean by that is that difference between those two is small. That means the difference between those two should be small as well. All right, so we're gonna go ahead and use the next example to approach it in the way we're gonna be focusing in our course, right? We're not gonna really dig in too much too formally here, but we're just gonna do basic type of problems. So let's try this example. Given the limit of 2x minus 5 equals 1 as x approaches 3, find delta such that the 2x minus 5, difference between 2x minus 5 and 1, is smaller than 0.01 whenever x minus 3 is smaller than delta. So this comes from here, and this comes from here, and they actually gave us this, right? This is your your epsilon. So all we have to do is actually find the appropriate delta that will give us this. Find the appropriate delta that will give us this. And so how do we do this? We'll actually start with that. Start with this. So start with this. What they gave you. Right? We want this to be true. So in a way it's like working backwards. So we want this to be true. We want this to be true. Right? So we're gonna sort of work backwards to have something of this form. Our goal is to have something of this form, because if we actually have something of this form, then this will tell us something about delta. And you'll see what I mean by that. So what we're gonna do here is start with what we're given and simplify, right? So this is 2x minus 5 minus 1 is minus 6. Right? I'm just doing basic algebra here. And I noticed that I added an extra 0, so let me fix that real quick. And there you go, right? So what we're gonna do here is we're gonna use that that rule from pre-calc that we learned. Do you guys remember that rule that if you have a function and that is set less than 3, then what this means is that you can drop the absolute values by setting the inequality on the other side, but changing the sign, right? So it's the same thing here. We're gonna drop the absolute value by setting the inequality in the same or on both sides of the function, and adding the negative. And then what you're gonna try to do is our goal is to make this look like x minus 3. And the best way to do this is by adding 6. Like add 6 here, add 6, right? So solve for x. So in other words, solve for x. And so that will give us 5.09, no, 99, and then 2x, and this will be 6.01. And then what we're gonna do, we're gonna divide both sides by 2. Divide both sides, or 3 sides by 2. And that, again, that will help us. And I meant 2. I don't know why I wrote the 3. That's so weird. 2, 2. There you go. And then so that will give us. This will cancel each other out, and so we end up getting 5.9 over 2 less than x less than 0.01 over 2. Now, if you notice, we almost have what we needed, right? Don't we just need a minus 3? So what we can do here is actually just subtract 3 on all 3 sides. So what we end up getting here is 5.99 over 2 minus 3 less than x minus 3 less than 6.01 over 2 minus 3. And I want to make sure I separate that right there. And there you go, right? You can see that this is the x minus 3 that we needed. In fact, we can go backwards from here to here, and we would have the absolute value now. The absolute value of x minus 3 will be less than 6.01 over 2 minus 3, which is roughly something about 0.005. And there you go. So we have, if we notice, we have exactly what we needed, right? We have exactly what we needed. We have that in here. So that means that this needs to be your delta. So this is your delta. So we found our delta. So we can see that the values need to be within 0.05. So what it means is that in order for this to happen, in order for this to happen, how close does x and 3 need to be? In order for this to happen, x and 3 need to be this close, right? The difference between x and 3 need to be this close. And that's pretty much it, right? That's pretty much it for this. You guys will have a few examples in the homework like this, and also kind of like the examples that we have above. So I hope that you guys find this helpful. I will be adding a few practice problems as well to give you guys a little bit more practice. All right, so we're gonna end here the section, and we'll jump into 1.3 next.